Hello everyone. So today I want to talk a little bit more about vector addition using our computational method that we used yesterday. Except instead of yesterday where we kind of half used a graphical method, used a concept builder with scaling already on it and a grid and a table, right? I just want to do this straight off math kind of way to do this, right? But I will kind of summarize our method as we go, and it's really going to be the same method as yesterday. So let's do one example together. Say you walk 15 meters west, and then you walk 12 meters at 30 degrees north of west. What is your overall displacement, your overall change in position? Well, to figure that out, we need to vectorially add these two vectors. So step one is always draw the vector diagram. 15 meters west would be an arrow pointing to the left. And then from the head of this arrow, we would draw the tail of the next one so that we could add them together. 12 meters is going to mean it's a little bit shorter than this one. 30 degrees north of west means we go out to the west and rotate 30 degrees north of that, like so. Now, if you're doing this, you don't have to draw it perfectly. It doesn't have to be drawn to a scale. You don't need a ruler and a protractor. You might want to try to keep it close, right? Just that you can kind of see what's going on. But we're going to do this computationally. That's one of the advantages, is that we don't need to be really precise with a ruler and a protractor. Our resultant displacement will go from the tail of the first to the head of the last, where we started to where we ended, the change in position. And notice here I'm just going to use a D for displacement. Now, this vector diagram, because we're adding together two displacements to find our resultant, is a triangle. So if you knew enough trig, you could use law of sines and law of cosines, but if we were adding more than two, right, we wouldn't be able to do that because we wouldn't even end up with a triangle shape at the end. So I want to use our more general component method that we learned yesterday, right? And our component method said, well, you take each vector and you break it up into components. This one is already all horizontal. So this one we could break up into a horizontal and a vertical component. And then we sum the x components. And then we sum up all the y components. And we end up with a vector diagram that is in the shape of a right triangle. Right? And then we can do the trig on it. Right? So that was the method that we used yesterday when doing the concept builder. So today I want to work that out kind of one at a time. What if we didn't have a nice grid to work on? What if we didn't have a table? Although you could feel free to draw out a table if you wanted to keep track of things that way. So first thing we have to do is to calculate the perpendicular components of each vector. Our first vector is pretty straightforward, right? It is all x, but be careful, right? These are vectors. This is to the left, which would make it negative. So the x component of our first vector, I'm going to call this dx1, right? The little 1 means this is our first vector. Doesn't really matter which order you go. After all, vector addition is commutative, but I got to label it something, right? So this is the horizontal component of our first vector is negative 15 meters. The y component is just 0 because it doesn't go up or down. There is no vertical part to it. Our second vector is a little less trivial. Here's our 12 meters at 30 degrees north of west. So here is our x component. Notice me call it dx2. Right? It's our second vector. And here is our vertical component, dy2. There's a little right angle here. Now we could use this 30 degrees, and then we would have to look at the diagram to decide whether the components are positive or negative, or we could tell the calculator we're in the second quadrant by using the angle from 0. Right, counterclockwise from 0, start here, right, over, that would be 150. Doesn't really matter how you do it, but you got to get the positives and negatives on there. So, to find the x component, we would do hypotenuse cosine of the angle. Again, you could use the 30 or the 150 in here. I use a cosine because it's the adjacent side to the angle. Right, cosine is adjacent over hypotenuse. If I plug that in, I get negative 10.4 meters. Negative, it's to the left, it's in the second quadrant. And you might note here that I kept an extra sig fig. I don't want to round all the time, right? Because sometimes you can end up over rounding. So I'm going to keep an extra sig fig in my calculations, and I will round on my final step when I'm coming to my answer. All right? To find the vertical component, well, that's the opposite side to the angle, so we would use hypotenuse sine of the angle. This one being up is, of course, positive. You might know the sine of 30 is a half, so it works out to be exactly 6.0 meters. Now, we could do this with 2 vectors. We could do this with 200 vectors. Get a little tedious, but we could do this, right? Break each one up into components. Being very careful about angles, positives, and negatives. Once we do that, we find the perpendicular components of our resultant by vectorially summing all the x's. We put all the x's together, which is a negative 15 meters and a negative 10.4 meters for a grand total of negative 25.4 meters, keeping the extra sig fig for now. And then we vectorially sum the y components. Right? So what we're doing here, notice, is we're doing the math behind the diagram we drew earlier. Right? So that's 0. This one doesn't have a y component. This one's a positive 6 for a grand total of 6.0 meters. This is basically the chart, right, that we had in the concept builder, except you don't have a nice scale on your page. You don't have a grid to use to be able to figure these things out. You got to do a little trig to do them instead. Once we have the components, our next step, well, we could try to do the trig on these, but it's a little hard to do the trig without a diagram. So I'm going to redraw my diagram using these components. So I'm going to draw the resultant vector diagram. Right? Since our x is negative, that's going to make it go to the left. Our y is positive, so that's going to make it go up. And there is our resultant, from the tail of the first to the head of the last. And notice we have a little right triangle. Now, remember, when I do these in my PowerPoints, they are all drawn to an internal scale. So compare this diagram to the original one. Right? And you notice it's that diagram, right? It's the same resultant, but now we actually know what the components are. Here we weren't sure how big this one was and this one was, but now we do. And that means we can do the trig. Little Pythagorean theorem to figure out the magnitude of the resultant displacement. And notice here I'm going to round off to 2 sig figs because that's what we had in our original data. And then we need to find an angle at the tail, always at the tail of the resultant. So we would use an inverse tangent. Tangent is opposite over adjacent. So it's an inverse tangent of opposite over adjacent. And we get an angle of 13 degrees. And then we have to name it. Well, if we go back to the original problem statement, right, this was done with cardinal directions, north, south, east, west. So let's do that in our answer as well. So our displacement would be 26 meters at 13 degrees, and notice this is west, so we have to rotate north of west. Okay, 13 degrees north of west, hope you're okay with that. West of north would be this way. Right? That would be west of north, this is north of west. If we were using counterclockwise from 0 notation, we would have to start here, that's 0, 90, 180 to get her all the way around, and then or halfway around, and then subtract off the 13, so it would be 167 degrees. I'm using north and west because that was in the problem statement. Right, so some of these you might see north, south, east, west. Some of these, like in your concept builder, we could use counterclockwise from 0 notation. So, a lot of math, right? Don't get lost in the weeds. If you can kind of think through what we're doing here, it'll help you, figure out all the parts. And then it's just a matter of doing the right math. So let me summarize. Right? Step 1, you draw the vector diagram. Right? Since we're adding, we draw the vectors head to tail, and our resultant goes from the tail of the first to the head of the last. Now, we don't actually do any math on this diagram, right? Unless it's already at a right angle, and then we can just jump to the trig. But this is really just to give us an idea of what the answer is. Right? I'll help you make sure that if you miss a positive or negative along the way, right, you'll see that it doesn't match your original diagram. Second step, we drew each vector one at a time and found its perpendicular components. First one was fairly trivial, but don't miss the negative here because it's to the left. Second one took a little more work. We could use the angle from 0 so that the calculator will spit out positives or negatives, or we have to look at the diagram or the quadrant. The x is to the left, that makes it negative. The y is up, so that makes it positive. Then we calculated the horizontal and vertical components of our resultant, right, by doing a little vector addition. Right, there's our x component. And then we did the y component. And then we drew our resultant diagram, right, from those components. And it was really the original one, but with a nice right triangle shape. And then we could do our trig, right, and name it. This is what we were doing, right, without using a grid and a chart and things to organize it, although feel free. Right? It really does it's kind of a nice way to end the unit, because it really does kind of use everything we've learned how to do. Right? Drawing vector diagrams, breaking stuff up into components, the right triangle trig. And notice that's all you need is right triangle trig with the component method. That's one of the advantages of it. Right? So all of that stuff so that we can start to do some vector algebra, and in particular, vector addition.